Testing. Okay, good evening. So it seems I haven't seen you guys for quite some time. So I'm sure you have enjoyed the national holiday, I guess. Anyway, so good to see you back. Okay, so I guess vaguely this is where we stopped last time. I think we were talking about the channel modeling, right, of microscopic fading. So we hope to just recap a little bit. So we hope to model the microscopic fading using a black box, right? So the black box enable us to figure out the output signal for whatever input signal we transmit, right? And then this we talk about from fading channel for terrestrial mobile fading channel. The system itself is linear, but unfortunately it's a time varying signal, a time varying system, because obviously the mobile is moving, the scatterers are also moving, right? So the response or the behavior of this multipath channel is not going to be static, right? So this time you observe the channel behavior at t equals 0, you get one behavior. At 1 minute later, you observe the channel behavior, you will get another kind of behavior. So this is a time varying system. But fortunately, this is linear. So we still can parameterize the behavior using a two-dimensional impulse response, right? So this is an extension of the linear and time invariant system that you have studied in your undergraduate, okay? In your undergraduate, if this is linear and time invariant system, the behavior of this LTI system will be completely characterized by a one-dimensional impulse response. And then that means knowing this one-dimensional impulse response, there is no more freedom in the behavior of this LTI system. But now the fading channel is a linear time varying system. So to completely specify its behavior, we need to know the two-dimensional impulse response, right? And then as we talked about last time, getting this two-dimensional impulse response is pretty difficult usually. So instead of talking about this two-dimensional impulse response, we try to capture some parameters, okay? So that knowing these parameters will enable us to get some first-order intuition on how this two-dimensional impulse response looks like. This is the same as in a coaxial cable. If you buy a coaxial cable, you don't often get the knowledge of the impulse response, right? Of course, you can measure this in the lab. But usually when you buy a coaxial cable, you only get some specifications such as the bandwidth, right? So bandwidth is one number, which knowing the bandwidth doesn't give you the entire frequency response, right? But knowing the bandwidth, you have an idea how the frequency response look like. Same here, okay? So, and then we mentioned that this t, the time variables, is used to denote the time variation dimension. And the time variation is driven by mobility, right? And this tau dimension is what we call delay. It's to capture the delay response. And this is still to induce by the multipath. That means the signal between there's more than one path from the transmitter to the receiver, and different paths land at the receiver with different delay. Okay, so that's why this is called delay response. Okay, so we'll talk about this two dimension independently. So we will introduce some parameters, some numbers. So knowing these numbers, of course, is not the same as knowing the entire impulse response. But similar to the concept of bandwidth, knowing these parameters will give you some idea how severe is the multipath. And knowing some numbers here will give you an idea how severe is the time variation. Okay? And that would be sufficient for our purpose. So let's look at this delay dimension, delay response. So one important parameter is called delay spread, denoted by sigma tau. Let's see. Okay, delay spread. So let me introduce what is delay spread first. So imagine this is a thought experiment. Imagine at the transmitter, you transmit an impulse. at t equal to 0. Okay, you inject an impulse, just like impulse response. And then this impulse go through this multipath. So at the receiver, some of this, imagine the transmitter is over that corner, I'm the receiver, okay? Suppose we ask that transmitter on that corner to send an impulse at t equals 0. So the first earliest path may be arriving the receiver, may be the line of sight, right? Because that's the shortest path. So I may receive something here. This is a line of sight path. Oops. This is a line of sight path, okay? The first arriving path, arriving with some delay here. But then this room, we understand there is also a non-line of sight path. So for example, the next path may be reflection from that wall to the receiver. I'm the receiver, right? So that second path will arrive at the receiver with a slightly longer delay. So that may be the second path, okay? And then the third path may be reflection from that side to the receiver. And that will take slightly longer, okay? So if you try to put down all the arriving path, arriving at different delay, right, you will see a profile like this. Now in general, we have an uncountably infinite many paths, right, arriving. So it's usually a continuum of arriving paths. So the picture will be you transmit a single very narrow pulse, like impulse at the transmitter. And then at the receiver, instead of receiving one impulse, you receive the aggregate of this multipath, each multipath arriving the receiver at different delay position. So at the receiver, you'll receive an aggregate like this, okay? So delay spread concerns about the range of multipath with significant power, okay? So this is called delay spread. Is that okay? So the longer the delay spread, the more severe the multipath in the environment. So that's the idea. Okay? So delay spread, if you have a large delay spread, that means you expect this propagation environment will have a huge multipath effect. Okay? Severe multipath effect. On the other hand, if the delay spread is small, then this environment may not have too many multipaths. Okay? This is one way to visualize this number. Is that okay? So this is the meaning of delay spread. So once again, when delay spread is large, we expect very severe multipath, right? What is the impact of huge multipath? We will talk about this later, okay? So I'm just talking about just some modeling. Here we're just still talking about the modeling, introducing some parameters to represent how severe the multipath effect is, okay? Now, with this understanding, so what can you say about the delay spread in indoor environment versus the delay spread in outdoor environment? Which one is larger based on this understanding? Is outdoor larger delay spread or indoor being larger? Outdoor, right? So usually this is larger, an order of magnitude larger. Now why is that? Well, we can imagine this the fourth experiment we talk about is just an indoor, right? So the delay spread will be depending on what? The delay spread in this indoor will depend on the size of this room, right? Because the contrast between the earliest arriving path and the latest arriving path will be determined by the, for example, the earliest arriving path is the line of sight. The longest arriving path may be 2-hop or 3-hop reflection in this room, right? So, but this contrast in the so-called delay spread, of course, depends on the size of this room, right? Now, imagine another thought experiment. If we do this delay spread measurement in outdoor, for example, the transmitter is, let's say, in the piazza, okay? And then the receiver is, let's say, in the front door of a library, okay? Then the earliest arriving path may be just the line of sight path, same as the indoor. But then the next arriving path may be reflection from the ground floor restaurant, right? The next arrival path may be reflection from the, buildings across the Clearwater Bay Road, right? You know, the next arriving path may be reflection from the IAS building, let's say, okay? So you see, because in outdoor situation, the scatterer basically exists over a larger dimension. So the differences between the earliest path and the latest path, the spread will be much larger. And that's the reason, usually, in outdoor propagation, the delay spread will be much larger than the delay spread for indoor. Okay? So in other words, delay spread depends on the size, the dynamic range, the spatial separation of scatterers. Okay? The larger the spatial separations of the scatterers, the larger the delay spread you would expect. Okay, so that's a number. So this number is easier, much easier to measure. And measuring this number gives you some statistical properties of the two-dimensional impulse response. So if you have a large delay spread, you expect this impulse response in the tau dimension will have longer tail, longer memory. Okay? You transmit an impulse, you see a lot of response extending over a large delay. Is that okay? All right, so this is delay spread, which is one parameter. Before I move to the other dimension, so there is another equivalent parameter that we can talk about in the multipath dimension. This is called coherence bandwidth. Coherence bandwidth, I will introduce what we mean by this. But coherence bandwidth is actually inversely proportional to the delay spread. So these two numbers, two parameters, only have one freedom. The freedom is the multipath dimension, okay? Because these two parameters are related to each other. So we only have one freedom. So what is coherence bandwidth? Now with coherence bandwidth, let me erase this. We imagine at the transmitter. In this case, it is the frequency axis. We transmit two pulses, two impulses in frequency. That means we transmit two single-tone signals. One has F1, frequency F1, one has frequency F2. Let's say they have unit amplitude. Okay? Now the first transmission at F1 at the receiver, we will receive a frequency. But then here, the response will be the aggregation of this multipath together, right? Like what we talked about last time. Is the mixture of constructive and destructive superposition together, right? So you have a certain fading coefficient, alpha 1, which is random, okay? The second transmission at frequency F2, when it reaches the receiver, you also have another response, alpha 2. So this alpha 2, once again, is a mixture of constructive and destructive superposition, right? Now, first of all, alpha 1 and alpha 2 are maybe different, okay? They are just two random responses. Now, why they may be different? Because last time, remember when we talked about constructive superposition, what's the condition for constructive superposition? You have two sine waves added together. When the path difference is integral multiple of a wavelength, then this is constructive superposition, right? So whether the result of this superposition is constructive or destructive depends on what? Depends on the wavelength, right? If it depends on wavelength, that means it depends on the frequency. Is that okay? So the response you get when you transmit a frequency F1 and the response for the same multipath, the response you get when you transmit at F2 may be different, okay? Because they have different wavelength in these two attempts. Is that okay? All right, with this understanding, so these are two random responses. When we talk about two random numbers, we can talk about a statistical measure called correlation. So we can talk about correlation. Correlation is the average of this alpha 1, alpha 2. Okay, this is called correlation. Now, for instance, if we have large correlation, when we have two random numbers, so correlation is a statistical measure to measure the similarity of two random numbers. Okay, so if two random numbers have high correlation, what does that mean? So if I have two random numbers, x and y, if they have high correlation, that means when x, the realization of x is large, there's a very high chance that the realization of y would also be large. This is called heavily correlated. Is that okay? On the other hand, if the correlation is very small, that means if I look at the realization of X, it is large. It doesn't affect too much the chance of seeing Y being large or small. If there's not much relationship, then the correlation will be small. Is that clear? Okay. So this is a number that a large correlation means alpha 1 and alpha 2, they will be simultaneously large or simultaneously small. Okay. If the correlation is small, then that means alpha 1 and alpha 2 are not related to each other. Okay. When one is large, it doesn't affect the chance for seeing the other being large or small. Is that okay? Now, so regarding coherence bandwidth, the coherence bandwidth, it turns out that, okay, I skip all the proof. Turns out that the correlation between alpha 1 and alpha 2 depends heavily on the frequency separation. The larger the frequency separation is, the less correlated they will be. Okay? So coherence bandwidth is the minimum frequency separation such that this correlation would be small. Is that okay? So that means if the frequency separation is sufficiently large, how large is sufficiently large? Larger than a parameter called coherence bandwidth, then the correlation of the fading response will be small. Is that okay? So this threshold, or the minimum frequency separation for you to see uncorrelated fading, is called coherence bandwidth. So this coherence bandwidth depends on the delay spread. So that means in the indoor propagation, delay spread is small, right? And that means the coherence bandwidth will be larger. So that means in indoor, like this room, we need to separate the frequency. In this experiment, we need to separate the frequency of the two transmission by larger separation in order for the fading coefficient to be uncorrelated. Okay? On the other hand, for outdoor propagation, delay spread is larger. So that means the coherence bandwidth for outdoor would be smaller, right? So that means in an outdoor situation, the frequency separation doesn't need to be that large, and I can still see the fading response being uncorrelated. Is that okay? So this is just a neutral statement. At this point, I didn't say anything about good or bad about uncorrelated fading. I'm just describing a phenomena. The phenomena is the correlation of this fading response will be less and less correlated as the frequency separation increases. Is that okay? Okay. So, and fundamentally, why the correlation depends on the frequency separation? That's because the condition for constructive and destructive superposition depends on the wavelength, and that in turn depends on the transmitting frequencies. Okay. All right. So for the multipath delay dimension, we have introduced two parameters: delay spread or coherence bandwidth. We talk about the meaning, and these two numbers are related to each other. Okay. Now, of course, if you look at the textbook or other materials, you will find that this the relationship between coherence bandwidth and delay spread, you have a different coefficient here. Okay. The ambiguity, because it is due to the fact that what do you mean by small correlation? In some textbook, they use 0.5 as the threshold for small. In some other textbook, they use 0.1. Okay. So these differences will cause differences in the coefficient of this formula. So it doesn't matter what is the coefficient. As far as this cost is concerned, you just need to remember they are inversely proportional. That would be fine. Okay? But be mindful that the coefficient behind the inversely proportional formula depends on what do you mean by small here. Okay? Do you mean 0.5 or do you mean 0.1? And you have different coefficients associated with this 0.5 version or 0.1 version. Okay? That's okay, right? I guess. So in a multipath dimension, you can either measure this delay spread or you can either measure this coherence bandwidth. Both are two sides of the same coin. The coin is to capture the multipath dimension. How severe is the multipath effect in the mobile fading channel? Okay. The other dimension, independent dimension, is the time variation. Similarly, we also want to introduce some numbers, some easy numbers, to quantify how severe is the time variation. The first parameter that people usually use is called Doppler spread. Doppler spread. Now, Doppler spread, you notice that this term Doppler, right? So in your high school physics, you probably come across something called Doppler effect, right? Do you remember what is Doppler effect? So if the transmitter is moving towards you, you are the receiver, and the transmitter transmits a certain frequency. So there is a red shift and blue shift, right? If the transmitter is moving towards you and sending you a frequency, your receive frequency will be blue shift, right? If the transmitter is moving away from you, and the transmitter is emitting some frequency to you, your receive frequency will be red shift, right? Is that okay? So that's called Doppler effect. And it's because of this Doppler effect that people, studying physics and astronomy figure out that our universe is expanding. Okay, how do they know the universe is expanding? They measure redshift in all directions. Okay, so what do we mean by? So this is the principle of Doppler effect. That means there is relative mobility between the transmitter and receiver, and this mobility causes a certain Doppler effect. Okay, but what do we mean by Doppler spread? So let me. By the way, in high school physics, the phenomena I just talked about, the Doppler shift depends on the speed over lambda. Okay, that's from relativity. So that means if you have a speed of v between the transmitter and receiver, and you are transmitting a certain wave with a wavelength of lambda, then the shift in the frequency the shift in the receive frequency will be given by speed divided by lambda. So that means the faster you move, the larger the shift will be. Is that okay? But then, what do we mean by Doppler spread? Let me erase this part. Now, Doppler spread is different from Doppler shift. So let me consider again a thought experiment. In this time, we have a transmitter sending a very narrow pulse in frequency, okay, a delta function in frequency. So let's say the transmitter sends a frequency F1, FC, okay. So at the receiver, now if you just have a Doppler, let me draw a scenario. For example, if this is the base station transmitter, the transmitter is sending a signal, a sine wave with carrier frequency FC, and then this is your receiver. Let's say the receiver is moving towards the base station with a speed of v. Okay. Now, the base station is sending a sinusoidal wave with frequency FC. Then in this case, the receiver will also receive a frequency, right? What will be the receive frequency in this case? What will be the spectrum received by the receiver? As we talk about, right? So this is the scenario where we have blue shift, right? So the receiver is moving towards the transmitter. So this is FC, but then the receiver will receive FC plus delta F, right? Where the delta F is the Doppler shift, right? Speed over lambda. Is that okay? So that is from your high school physics. So I guess the other toy example in your high school physics is not for the electromagnetic wave, but sound wave, right? So if you have an ambulance sounding a horn traveling towards you, you will receive a higher pitch, right? If the ambulance is moving away from you, you will perceive a lower pitch, right? So that was a typical scenario that Doppler effect was introduced for the sound wave. So the same applied, the same Doppler effect exists in electromagnetic wave as well. So that's why there is a blue shift. You shift to a higher frequency due to this relative motion, right? This is Doppler shift. However, in a mobile communication channel, when you perform this experiment, the received spectrum, you will receive something, not just this guy. You will receive this one together with this one. So in fact, you will receive a lot of components. So you transmit a single tone frequency, but at the receiver, you receive a whole range of frequencies. So that's why it's called a Doppler spread. It's not Doppler shift. It's different from Doppler shift. It's a spread. So this is a dual situation compared to delay spread, right? When we talk about multipath, in delay spread, you transmit a narrow pulse in time. at the transmitter. But then at the receiver, you receive a whole range of echoes arriving at different delay position. So it's a spread in the delay dimension. Here, you transmit a narrow pulse in frequency, a single tone frequency at the transmitter. But at the receiver, you receive a whole range of frequencies. So that is a spread in frequency. So the two sides, the two effects are symmetrical with each other, but just one in the delay dimension, the other in the frequency dimension. Is that okay? So, but let's try to understand the physics first. Now, in this scenario, we understand we will receive this, right, from high school physics. But how come we receive other components as well? How comes the receiver will pick up other components simultaneously? Understand my question? This component can be understood by double shift, right? Because now the receiver is moving towards the transmitter, just like you are moving towards the ambulance, right? So you perceive a higher pitch from the ambulance, right? Doppler effect. But why at the same time you receive the other lower pitch and other some components in the intermediate? What's going on here? The reason is because there is multi-path as well, right? So this is just one path, direct line of sight path. So this path experience a blue shift. So that's why your perceived frequency coming from this path will be higher, landing here. But this is not the only path, right? You may have another path due to an obstacle, reflection from the back. This is a second path, right? With respect to this second path, this is like a mirror. This receiver is like moving away from the transmitter with respect to the second path. So this second path will contribute a redshift here. Is that okay? And then there will be some other intermediate scatterers. For example, the third path may be like this. And if you recall from your high school physics, it's not the speed, it's the transverse speed that will contribute to the Doppler spread. So if the third path arrives at the mobile at an angle, it's the V cosine theta, okay, V cosine theta, this component that will contribute to the Doppler effect. Is that okay? So the cosine theta, theta is the angle of arrival, which is also random due to the different scatterer. So this third path may end up having here, okay, and the fourth path may be here. So if you imagine you have many paths, each path will contribute a different Doppler effect, a Doppler shift. So you put all these paths together, you get this entire spectrum. Is that okay? So that's the reason why you receive more than one frequencies at the receiver. This is due to the aggregate effect of Doppler shift and multipath. Each path experiences a different Doppler shift. Is that okay? So collectively, you get this whole thing. This is called Doppler spread. Okay. Now later on, after we finish this part, I'll give you a case study. In the case study, you will see Doppler shift and Doppler spread are different things. Okay. When you experience Doppler shift is something you can be compensated. Okay. But for Doppler spread, it's not something that you can easily compensate for. Okay. So these are different things. And here, this picture corresponds to Doppler spread. Okay. And Doppler spread comes from multipath. Okay. So anyway, so this is a number, a parameter. When the larger this Doppler spread is, the more severe the time variation effect would be. Okay. And of course, this Doppler spread depends on the mobility, the speed. Okay. So it depends on the environment. If you are on a vehicular environment, let's say you are traveling on a train or MTR, versus a pedestrian mobility, that is, you are holding your mobile walking. These two groups of users will experience different Doppler spread. Which one will be having a higher Doppler spread? Of course, vehicular user will have higher Doppler spread, right? Because the speed is higher for vehicular user compared to pedestrian user. So later on, we will see that if you have to design a system for pedestrian user, just like Wi-Fi, versus designing a system for vehicular user, just like GSM or 3G, they will have different effect, and you will require different solutions. Okay. Okay. Anyway, so this is one parameter. A second Similarly, a second parameter, which is basically related to this parameter, is called coherence time. Now, again, coherence time is inversely proportional to the Doppler spread. Okay, they are not independent. Now, what is coherence time? Coherence time is, let me erase this. Again, let's imagine an experiment similar to coherence bandwidth. Now, at the transmitter, we transmit a level pulse in time. T1, 1 unit, and then T2, 1 unit, okay? So, at the receiver, we will pick up two responses. One has a response, fading response alpha 1. The other has a fading response of alpha 2. Alpha 1 and alpha 2 are two random responses, okay? Now, again, we want to use the correlation to measure how similar these two random numbers are, okay? And we also know that the larger the time separation is, the less correlated they would be, okay? So, therefore, we have the same thing. If the time separation is sufficiently large, how large is sufficiently large? Larger than a parameter called coherence time. If the time separation is larger than this coherence time, then this correlation of the two fading will be small. Okay? The other way to look at that is if the time separation is not small. Okay? If the time separation is small, very small, much smaller than this coherence time, then in this case, the correlation will be very large. Large correlation means if you observe alpha 1 to be large, there's very high chance that alpha 2 would also be large. That is called high correlation. Okay? On the other hand, if the time separation is larger than this coherence time, then the correlation will be weak. That means if you look at the realization of alpha 1, let's say it's large, it doesn't affect too much the chance of seeing alpha 2 being large or small. Okay? Just like to go to casino, you roll two dice. Okay? The first dice is not correlated with the second dice. So even if the outcome of the first dice is large, it doesn't affect the probability for the second dice to be large or small. This is a situation of small correlation. Is that okay? Now, if you still have questions about the concept of correlation, so let me give you a toy example. So let's say someone tells you that, let's say you are superstitious. Okay, let's say someone tells you that on the examination day, if you wear a red T-shirt, you will have a higher chance of getting distinction. Okay, so let's say some fortune teller tell you that this date is good for you. You wear a red T-shirt, you have good luck and whatever. So how do you test whether this is true or not? Well, statistically, we can do a test, right? We can, on the examination day, we can take samples, right? So we can define X belongs to +1 or -1. If you wear a red T-shirt, I give you +1. If you wear not red, other than that, you get a -1. Okay, and then Y is your score of the midterm of the final examination, and then I can try to compute the correlation between these two things, right? Let's say I have 100 students in the class. I compute this guy. So this is the correlation, right? If it turns out that this correlation is large, then what does that mean? That means there are certain truth behind that statement, right? So those who wear red T-shirt indeed has a higher chance of getting distinction, okay, if the correlation is large. If the correlation is small, then that means there's no relationship, right? Okay, so correlation is used to study this kind of two random numbers. Are they affecting each other? Okay. Now, but in fact, I don't want to sidetrack too much, but you know that, let's say they have high correlation. Correlation doesn't imply causation. You understand what I mean? If XY has high correlation, doesn't mean X is the cause for Y. Okay? So, but you can counter-argue. What do you mean by causality? Okay, so actually in philosophy, we all assume we have causality, right? When when you study hard, you get distinction, right? So causality. But in fact, in philosophy, it's not universally accepted that this world has causality. But this is sidetracked too much. So some modern philosopher actually do not need to worry about causality. They just work on correlation. Okay, they doesn't need to worry about what is the cause of what, and it doesn't matter at all. So what you actually need to know is whether these two things have high correlation or not, and that would be sufficient for practical purposes. But anyway, so that's the meaning of correlation. Is that okay? So here, alpha 1 and alpha 2 are just two random numbers. So we want to see whether these two random numbers are similar or not related to each other. So the way to study this is to look at the correlation. It turns out that if the time separation is large enough, then these two numbers, alpha 1 and alpha 2, are not related to each other. Okay, the correlation would be small. Is that okay? So how large is the time separation needed for you to observe uncorrelated fading? This threshold is called coherence time. And this coherence time is inversely proportional to the Doppler spread. Okay? So that means for pedestrian user, if you're holding a mobile walking, for pedestrian user, the Doppler spread would be small, right? Because the speed would be small, right? So for Doppler spread being small, so that means the coherence time for pedestrian user will be large. So that means if you're a pedestrian user, the time separation needs to be larger in order for you to see uncorrelated fading, compared to, let's say, vehicular user. If you're a user traveling on MTR, on a train, the Doppler spread will be larger, and therefore the coherence time will be smaller. So for those traveling on a train, you just need to separate the time by a little bit. Okay, much smaller time separation will be enough for you to see uncorrelated fading. Is that okay? So that's the effect. And once again, although I introduced two numbers, you only have one freedom. Okay, the freedom is this time variation driven by mobility. Mobility refers to mobility of the mobile or mobility of the scheduler. Okay, so is that okay? So with these two dimensions, of course, this for each dimension we introduce two parameters. For the multipath dimension, we talk about delay spread or coherence bandwidth. These two are related to each other. Okay. For the time variation dimension, we talk about Doppler spread or coherence time. Again, these two are related to each other. So altogether, we have these two independent dimensions. Knowing these parameters does not give you a precise description of the fading channel. Okay, but it gives you some idea, some qualitative idea, how this two-dimensional impulse response will look like. Okay, so now based on these two parameters, we can actually partition into four situations. So let me erase this. So this axis is used to measure multipath. Let's see if this is multipath. In the notes, this is time variation. This axis is to measure the multipath effect. Okay? So, and we need some parameters. So we partition this time variation into two parts. Okay? Let's say we define the threshold here. On this side, we call this fast. This is slow. Okay? So what do we mean by fast? So here, if we use symbol duration, and then this threshold is the coherence time. So fast means what? This region means the symbol duration. The symbol duration is the duration of a modulation symbol. We talked about several lectures ago. This region means a symbol duration is much larger than coherence time, right? So what does that mean? If the symbol duration is much larger than coherence time, that means when you transmit a symbol, when you transmit a modulation symbol, okay, let's say this is a transmitter, the fading response that you see in this beginning of the symbol and the end of the symbol, these two fading response, alpha 1 and alpha 2, will be will be uncorrelated, right? Will be uncorrelated. So that means if this alpha 1 is large, it doesn't affect the chance for alpha 2 to be large or small. Okay? So that means within the modulation symbol, you see a potentially different fading response. Okay? So somebody call this fast, somebody call this time selective. Okay? They are equivalent. On the other hand, on this side, that means the symbol duration is much less than the coherence time. This is called a slow fading, okay? Or, well, let's say called time slow fading. So this slow fading corresponds to this scenario. At the transmitter, if we transmit a symbol, okay, a modulation symbol with duration Ts, just according to this region, this coherence time is much longer than the symbol duration, right? So let's say coherence time is this long. So that means what? That means within the symbol, you are going to respond, the fading you are going to see is heavily correlated. Alpha 1 and alpha 2 are with high chance to be the same, right? So if alpha 1 is large, there's a very high chance that alpha 2 would automatically be large because that's the meaning behind high correlation, right? So within a symbol duration, the fading response is almost flat. So this is alpha t. Okay, so that's why this is called slow fading, or another adjective for this is called time flat fading. Time flat means that the fading response is almost quasi-static within a modulation symbol. That means when you transmit a symbol, the entire symbol will experience only one alpha, only one response. This is in contrast with this, right? In here, when you transmit a modulation symbol, this is a modulation symbol with duration Ts. Within a modulation symbol, the symbol is going to experience different fading within the symbol. Okay? So you will have a different distortion associated with these two effects. So the boundary between fast and slow is you need to compare the transmission parameter, Ts. Ts is your transmission parameter. Tc is your channel parameter. Okay? So Ts depends on how your modulator is designed, right? Tc depends on what? Depends on your mobility, coherence time. Okay? So this is the environment. This is your transmitter. You need to compare against these two parameters before you can tell whether you experience fast fading or slow fading. Is that okay? So that's the time variation axis. On the other hand, the y-axis, multi-path dimension. Again, we want to partition the y-axis into two parts. So let's compare between. So on this part, let's say, what do we call this? We call this flat fading, frequency flat fading. Okay, so this side corresponds to the situation you don't have too much multipath. Okay, so here in the notes, I'm using, again, symbol duration here. So here, so this region corresponds to the symbol duration much larger than, this is the delay spread, this threshold. Or let me, actually, it's easier to use another parameter. Let's say this is coherence bandwidth, and then this is your transmitted bandwidth. So this region corresponds to the coherence bandwidth much larger than your transmission bandwidth. Okay? On the lower side of this axis, this corresponds to what we call frequency selective fading. So in terms of parameter, this corresponds to the coherence bandwidth much less than the transmission bandwidth. So these are the two regions. Now, let me explain why this is called frequency flat fading. Now, if you transmit a signal, now let's look at the spectrum of your transmitted signal. Let's say this is the signal you transmit with a certain bandwidth. Okay? Now, in this region, the coherence bandwidth is much larger than your transmission bandwidth. So let's say this is the coherence bandwidth. And this is your transmission bandwidth. So that means when you transmit the the first frequency component in your transmitted signal, it will experience a certain fading coefficient, alpha 1, right? In the end of your spectrum, when you transmit the last component, you will experience a fading coefficient alpha 2, right? So the frequency separation within your transmitted spectrum is much less than the coherence bandwidth, right? So what does that mean? That means you expect the correlation between these two fading response would be large, right? So what do we mean by large? That means if alpha 1 is large, there is very high chance that alpha 2 would also be large. So that means if you try to draw the frequency response would be like this, almost like a flat line. So that would be the frequency response in terms of the frequency. Okay, so that means within your transmitted spectrum, within your transmitted frequency components, all the frequency components experience very similar fading. So that's why this is called frequency flat. In response to the transfer function of the fading channel is like a flat response. Okay, that is because all the frequency components within your transmitted spectrum experience very similar fading. Why very similar? Because they have high correlation, because they are within your coherence bandwidth. Is that okay? So that's what happened in here. Now what about here? On the bottom side of this y-axis, frequency selective fading. This is the opposite. Let me draw on this side. If this is a transmitted spectrum, once again, this is the bandwidth. Okay? But in this case, let's say the coherence bandwidth is very small. Let's say this is the coherence bandwidth. Okay? Then what happens is, in the first frequency components that you transmit, it may experience a certain alpha 1, right? At the end of your transmitted spectrum, you may experience another frequency fading coefficient. Now in this case, the fading coefficients are uncorrelated. What does that mean by uncorrelated? That means if you look at alpha 1's realization, let's say alpha 1 is large, it doesn't affect the chance for you to see alpha 2 being large or small. Alpha 2 can be small in general, right? With high chance. So that means if you try to plot the response will look like this. So that means within your transmitted spectrum, all these transmitted frequency components may experience different fading response. So that's why this is called frequency selective. The term selective means the response is not flat. You will have different fading response according to different frequency components that you transmit. Is that okay? So because of that, a little bit chaotic here, so we can partition into 4 situations. The y-axis and the x-axis are 2 independent dimensions, right? Once again, the x-axis is time variation driven by what? Driven by mobility. The x-axis is basically talking about multipath. Okay, so these are 2 independent dimensions. So each axis have 2 situations. So 2 times 2 means we have 4 situations together. So which 4 situations? On this side, we have fast. Fast refers to the time variation, right? Fast flat fading scenario. Flat fading corresponds to frequency flat fading, okay? On this side, so this is the fast frequency flat fading channel. On this side, this is slow frequency flat fading. Is that okay? On this side, this is fast frequency selective fading. And this is slow frequency selective fading. Is that okay? So we just 2 times 2. 4 combinations of this adjective, right? X-axis give you fast or slow. Y-axis give you frequency flat, frequency selective. So you just combo this together, you have 4 situations, okay? Now, I'm going to, with a leap of faith, I'm going to tell you which one, so each of these situations will cause different troubles to the physical layer. Troubles means different impairments. So if I have to assign different number of stars to represent the difficulties. This situation, slow frequency flat fading, will give you 1 star of trouble. Okay? It will still have some impairments, but relatively easy to deal with. This second situation, fast frequency flat fading channel, it worth 2 stars of trouble. Okay. And then this guy, slow frequency selective fading. Again, 2 stars of trouble. And this guy, fast frequency selective fading, give you 3 stars of trouble. This is the most difficult case. Okay. Now, I will explain what we mean by number 1 star, 2 star later on. Okay. But this is just to give you an idea. So before you remember the day one, I talked about communication system, right? I say that the first task as a communication system engineer, the first thing you need to do is not to design the transmitter or receiver. What's the first thing you need to do? You need to understand the channel, right? So we talk about additive white Gaussian noise channel, which is relatively simple. And then now this is the second channel we talk about. So the first thing we need to do, which is what we are doing, is to understand the channel. So we build channel model to model this multipath fading, right? And based on this channel modeling, we can partition into 4 situations. We need to first understand which situation we operate before we attempt to design the transmitter and receiver. Because these different styles of trouble will have different impairments, and they demand different solution roadmap. Okay? So once again, there is no universally optimal design that can work for all situations. So if you are a good system engineer, you need to first understand what is your operating region. Okay? Now, just to give you an idea, so in this course, we won't talk about fast fading. So these two sides, we won't. So these two sides, we won't worry about these 2 things. We only worry about this one and this one. Okay. The reason is because if you look at this for practical system, this side is what the symbol duration is much larger than the coherence time, right? So let's look at some practical values. For 4G, 5G, the mobility of the user we are talking about is something like bullet train, high speed rail, right? So which is something around 300 km per hour. If you do the math, 300 km per hour corresponds to the coherence time is of the order of millisecond, something around 1 millisecond. Okay, so this is around 1 millisecond for cellular communication. And for cellular communication, the symbol duration, let's say you take 4G, 5G, this symbol duration is of the order of microsecond. Okay, so that means we are well into this region. Okay, so this is millisecond, this is microsecond, this is millisecond. So we are well into this operating region. So we don't need to worry too much about the psi. Okay. When will we need to worry about the psi? For example, if you are designing something that we know these days low orbit satellite is very popular, right? We have Starlinks and this and that, right? So a lot of low orbit satellites. If you are designing communication between 2 low orbit satellites, their mobility is much higher than the vehicular mobility we're talking about. Okay, so if that's the scenario, you probably need to worry about this scenario. Okay, or if you're designing communication system between the airplane and the satellite, that sort of scenario, then you may need to worry about this region. But since these are not the focus in our course, so we won't talk about the fast fading case. We will only focus on the slow fading case. And in the slow fading case, we still have 2 cases. The first case is slow frequency flat fading. Okay, that is you don't have too much time variation and you don't have too much multipath. One way you can interpret it this way. So when you have this scenario, this will give you 1 star of trouble. I will explain what exactly is this 1 star of trouble in a minute. Okay. When you have this situation, slow frequency selective fading, that means you don't have too much mobility issue. Okay, it's still relatively speaking slow mobility, but the multipath dimension is much more severe in this second case. So it will give you 2 stars of trouble. Okay, and again, I will explain exactly what are the 2 stars of trouble, and then each of these situations demand a different solution roadmap, as I explained. Okay. So, and this will be the most relevant scenario that we need to worry about for designing cellular networks in terrestrial applications. Is that okay? All right, so if you later on, after you graduate, you work for a chipset designer or you work for Huawei, as a equipment vendor designing the chipset or physical layer, you need to worry about what situation your system needs to operate on. Okay, so you need to go through this analysis, and then based on this analysis, you will define or you will have to embrace different solution roadmap, which I'll explain in a minute. Okay. So once again, you will see later on that the solution for this case may not work for this case. Okay, so they are different. Now, of course, if you work for operator, then you don't need to worry about this at all, because if you work for operator, you just buy the base station. You don't have the freedom to open up the base station and work on the physical layer. Okay. Okay, so let's drill into the first case. Now, without loss of generality, we will always assume the time mobility psi is slow fading. Okay, so without even mentioning slow all the time. So we just drop the adjective, assuming that it is slow. Okay, and slow means when you transmit the modulation symbol, the entire modulation symbol will experience uniform fading. Okay, that is what we mean by slow. So that means you don't have too much distortion on your transmitter symbol. Okay, that is to say. Okay, so let's zoom into this one-star trouble, the easiest case. So this is also affiliated with narrowband transmission, because you look at this condition. This condition corresponds to what? The transmission bandwidth is much less than the coherence bandwidth. Once again, transmission bandwidth is your transmission parameter. It's determined by your design of the transmitter. Coherence bandwidth is determined by what? It's by your environment, whether you are indoor or outdoor. Okay. So when you operate in this situation, your transmission bandwidth is usually smaller than the coherence bandwidth, and that usually corresponds to something called narrowband transmission. The transmission bandwidth is small, and that is also intuitively conform to your intuition, because if I ask you to design a communication system that has to deliver wideband signal compared to delivering narrowband signal, your intuition will, hopefully you will understand designing a wideband transmission system will be more difficult, more challenging than designing a narrowband transmission system, right? So, and that's the reason, one of the reasons for this intuition. When you have a narrowband system, you are likely to hit this frequency flat fading case. So that means you are likely to hit this one-star trouble only, okay? So, now with this one-star trouble, let's zoom into this. So, frequency flat fading channel. So one way to look at that, the condition is, as I said, right, the transmission bandwidth is much less than the coherence bandwidth, okay? Or equivalently, you can say transmission bandwidth is 1 over TS, right? Coherence bandwidth is 1 over delay spread, right? So that means the delay spread is much less than the symbol duration. Is that okay? These are equivalent to each other. So let's try to visualize the time domain process. So at the transmitter, let's say you transmit a symbol with a duration Ts. Okay? Now, the physical channel, you still have multipath. You still have multipath. So you may have the first path giving you a certain delay, second path giving you a certain delay with different response, all the way to, let's say, 1,000 path. Let's say you have 1,000 path giving you a certain delay. But this delay spread, this is the delay spread, right? The delay spread is much less than the symbol duration. So what does that mean? That means when you add up this multipath, the overall received signal, you transmit one symbol. At the receiver, you perceive one symbol. You also receive one symbol as well. But that symbol will be slightly distorted, okay? So that would be the intuition. So here I need to introduce a concept called resolvable path. Or resolvable symbol. So although physically you still have 1,000 multipath between the transmitter and receiver, but since the delay spread is much less than a symbol duration, so even though you add up all this effect of this 1,000 multipath together, the receiver still perceives as one symbol. Okay? This is like acoustic. Let me give you an acoustic toy example. Let's say after class, you can give it a try. If you go to the staircase, I guess this is, so outside the classroom, you have a staircase, right? If you go to the staircase and start talking to yourself, let's say you say a letter A, right? Due to the reflection from the staircase, the walls of the staircase, right? The staircase is very small in volume, right? So that corresponds to the small delay spread situation, okay? So the acoustic delay spread in the staircase is pretty small. So when you say a letter A, you will hear your voice as, when you say one symbol, A, you will still hear your echo as one symbol, right? You can imagine this, this toy example, right? So when you say a letter A, you hear your voice as A, but your received voice will be slightly distorted, right? So that corresponds to single resolvable path. The number of resolvable paths is actually given by delay spread divided by symbol duration. Take the ceiling, okay? Or equivalently, transmission bandwidth divided by coherence bandwidth. What does that mean? So if, on the other hand, if you don't go to the staircase, you go to some rural area where you have two cliffs facing each other. And then let's say this is you. And you start to say a letter A. In this case, can you imagine what will you hear? Your transmitted sound wave will get bounced back and forth multiple times, right? So you'll start hearing your voice as A. Can you imagine this? Okay? That corresponds to the case where you do not have, you have more than one resolvable path. Okay? Because the delay spread in this case is much larger than your symbol duration. So when you transmit one symbol, you'll perceive as 4 distinct symbols on the receiver. Okay? Whereas in this case that I'm talking about, the delay spread is so small. Now in both cases, you may be affected by the same 1,000 physical multipath. Okay? But what matters is your perceived number of symbols. In the first case where your delay spread is very small, compare to your symbol duration, like the staircase scenario. When you say a letter A, after you aggregate all these 1,000 physical multipath, you still hear your voice as one single letter A. Is that okay? Whereas in the second scenario, if you go to some rural places like in Saikong, you may be affected by 1,000 multipath. But in this case, the delay spread is much larger than your symbol duration. So when you say a letter A, you'll hear your voice as multiple echoes, multiple resolvable echoes, A. Okay? So in both cases, you may have the same physical multipath, 1,000 multipath. The only difference is in the second case, the delay spread is much larger than your symbol duration, whereas in the first case, the delay spread is much less than your symbol duration. So the perceived effect will be different between these two cases. Is that okay? So I hope you know what I'm talking about, right? If you still have questions, so after class, you try to go to the staircase and start to talk to yourself and see, perceive what happens to your voice when you start talking to yourself in the staircase. Okay, but you have to do this one by one. If you still have confusion, there is also another example I can think of. I'm sure you must be very good at KTV, right? Karaoke. So if you go to karaoke, you know there is an echo, right? So somebody would like to tune up the echo when you sing. This echo is adding artificial multipath to your voice. But you don't want to tune up the echo too much, right? If you tune up the echo too much, then when you sing a song, when you say a letter A, your voice becomes A. Then it's very difficult to sing a song. So in KTV setting, the artificial echo they add, they make sure that the delay spread is much less than your symbol duration. So when you say a letter A, you still perceive your voice as one single letter A, so that your voice will be distorted in a more favorable way. Okay, so that is another example of acoustic multipath added to with this scenario. Is that okay? All right, so let's focus on this. So in this first situation, frequency flat feeding channel, you only have one resolvable path, okay, or one resolvable symbol. Now, although you have one resolvable symbol or path, somebody calls it symbol, the actual number of physical multipath is still plenty, okay? So once again, you still have 1,000 physical multipath behind this one resolvable symbol. Is that just that the delay spread is much less than your symbol duration. So you cannot resolve this 1,000 path as individual path, okay? So now with this frequency flat fading channel, we can approximate the channel model as like this. If we transmit a symbol X, the received signal will now be given by some fading coefficient alpha, which is random, times your X plus the channel noise. Now, so this is different from additive White-Gaussian noise. In additive White-Gaussian noise channel, there is no alpha. What you receive is the transmitted symbol undistorted plus the channel noise. Okay? So now with this flat fading channel, what you receive is a certain distorted transmitted symbol, distorted by this fading coefficient plus the additive White-Gaussian noise. So there are two independent random processes in the channel. One is the channel noise. The second is this fading coefficient. These two things are random. Okay? So that is the additional effect due to this so-called frequency flat fading effect. This is coming from physically, coming from the multipath. Okay? So physically, this is coming from the overall effect of the multipath combination of constructive and destructive superposition. Okay? So when this alpha 1 magnitude is large, that means you are in bright spots. When this alpha 1 magnitude is small, that means you are in dark spots. Okay? So that accounts for this kind of fading effect. Is that okay? So that will be the channel model. So when you transmit one symbol, you will receive a distorted symbol plus noise. That's what this channel is telling you. So one resolvable symbol. Transmit one symbol, you will receive as one symbol, okay, plus noise. Now with this, so this is what this frequency flat fading channel is giving you, the one-star trouble. So now let's look at what exactly is the trouble, one-star trouble. Okay, so we talk about digital modulation, right? So let's say you use a just simple binary modulation, BPSK, right, for example, to send the symbol to the other side, but over a frequency flat fading channel in between. Okay, so let's say this is your transmitter, BPSK. You transmit this BPSK symbol through this frequency flat fading channel. That means the received signal is equal to fading coefficients times your transmitted signal plus noise. And then this is the receiver. Okay? Now let's consider this situation. You are not doing any redesign. You just transmit the good old binary modulator, BPSK modulator, and you use the minimum distance demodulation at the receiver, but just over a different channel. Instead of additive White-Gaussian noise channel, you transmit over this frequency flat fading channel. So let's look at what is the impact to the performance. So the way we measure performance is, this is error probability, and this is the signal to noise ratio, right, in dB. So as we talk about in additive White-Gaussian noise channel, what do you expect to see? How would the error probability depends on signal to noise ratio? It will be a curve like this, right? Because that means as you increase the signal to noise ratio, you expect the error probability to drop, right? That's because when you increase the signal to noise ratio, you can move the noise cloud center further apart, right? When you move them further apart, the overlapping area decreases. So the error probability decreases. Is that okay? So that's the mechanism. And usually this is in log scale. This is also in log scale. So if you're talking about additive White-Gaussian noise channel, so this is additive White-Gaussian noise channel. The curve will be like this. And if you are talking about very high signal to noise ratio, the asymptotic slope will be almost vertical. So that means this curve will be very steep. Now, what do we mean by having a very steep curve like this? That means this is delta SNR. This is delta PE. That means if you have a very steep slope, this is good because that means you just need to increase the signal to noise ratio a little bit, and then you will bring about a huge drop in error probability, right? In other words, the error probability is very responsive to your signal to noise ratio. When you increase the signal to noise ratio a little bit, the error probability drops a lot. Is that okay? So this is good, right? So for additive white Gaussian noise channel, this can be shown to be having this behavior. But now, here is the one-star trouble. If you just keep the same design, same modulation, same receiver, but now you apply this to a flat fading channel, where you have this additional fading coefficient, which is random, right? Then you do the simulation and you plot the error probability. The error probability still decreases as you increase SNR. However, the error probability curve will be decreasing much slower. Asymptotically, this becomes a straight line. Okay? This becomes a straight line with a certain slope. So this is frequency flat fading. And that's the one-star trouble. That means if you do not do anything about this, the impact of operating in frequency flat fading channel is that your error probability curve drops slowly with increase in signal to noise ratio. So what does that mean? That means, is this good or bad? Of course it's bad, right? Because if I want to, let's say to support voice communication, let's say a certain application will demand a certain target error probability. For example, voice application will demand a target error probability of 1%. Okay, we will explain this in the next chapter. So for 1% target, if you just have an additive white Gaussian noise channel, no fading effect, you just need this amount of signal to noise ratio or transmission power. But now, with everything remains to be the same, if you just, to maintain the same error probability target of 1%, now when you operate in frequency flat fading channel, you will need this much of signal to noise ratio, right? In other words, this difference is the SNR penalty. It's a penalty, right? So let's say if this is, I don't know, 20 dB. If this is 20 dB, what does that mean? That means if I'm talking about in the context of cellular operator, that means in order for me to maintain the same coverage as before, I need to increase the power amplifier by 20 dB more power, right, if I can, to keep the same range. Or if I cannot change the power amplifier, that means I need to take away 20 dB from my link budget. That means my coverage will shrink. Is that okay? So that will be the penalty. Okay, so obviously the penalty, the immediate penalty is coverage. If you work for operator, so, and you know that, okay, this particular market has frequency flat fading effect in between the base station and the mobile, then the impact would be, in this example, you need to take away 20 dB from your link budget. If you take away 20 dB from your link budget, that means your coverage of the base station will shrink. Maybe initially, for additive white Gaussian noise channel, the base station can cover 2 kilometer radius. But if you do not increase the transmission power, when you operate in frequency flat fading channel, the coverage of this base station may shrink to, I don't know, 500 meters. Is that okay? So that is the one-star trouble that I'm talking about. Okay? Now, one-star trouble doesn't mean you can ignore this. Okay? Most of the time, you cannot ignore this. Now, you may argue, okay, for coverage consideration, now, if I can increase the transmission power, if I can upgrade the power amplifier in the base station, I may be able to absorb this 20 dB loss, right? But later on, we will see that, for example, in CDMA network, this 20 dB SNR penalty will also translate to capacity penalty as well. And as I briefly mentioned, cellular network is a interference limited system. That means for capacity consideration, you cannot improve the performance. You cannot ignore this one-star effect by just increasing power. Increasing power can help you with the coverage, but it cannot help you with the capacity penalty. Okay, so so that means you need to do something about this. Any questions? Moreover, notice that these two curves have different slope, right? So this SNR penalty can be arbitrarily large, depends on your target error probability. If for some other application you need a lower error probability target, then this SNR penalty is going to be larger and larger. Okay, so fundamentally, okay, so let me do it this way. Now, so this is talking about one modulation scheme, right? Can I change the modulation scheme? And so that is a one-star trouble. So then the next is talking about then what can we do about this? What is the solution roadmap, right? So one solution roadmap you can think about is, perhaps can I change to another modulation constellation, right? Because I have freedom to design a modulation scheme. Now, it turns out that if you change the modulation scheme, you have some impact. The impact is the error probability curve may be shift like this. So these three curves are different modulation scheme. Okay? So by using more robust constellation, you may be able to shift the error probability curve towards this side. Okay? But their slope is equally back. So that means this kind of solution, by changing modulation, you only get a horizontal shift. This horizontal shift is what we call a second order benefit because it doesn't solve the first order problem. The first order problem is the slope is different. Is that okay? So giving you a certain fixed gain, it's just a horizontal shift doesn't help much, especially if you're operating at high SNR. Okay? So these are changing the modulation scheme just a second order solution. So we need to look for first order solution. So what is the first order solution? You see from here, diversity. Okay? We need to exploit diversity. So diversity is our solution roadmap. So we'll talk about diversity. What is diversity? We have been, I guess I'm sure you have been practicing diversity all the time without even realizing this. For example, let's say after you graduate from MSc, you need to look for jobs, right? When you look for jobs, will you just send out one application? Probably not, right? Unless you're super confident. You tend to send out multiple applications, right? Why? Why you want to send out multiple applications? Because you think that will enhance your chance of getting an offer, right? That is diversity. There is one hidden assumption, very important assumption for this to work. What is that assumption? When you send out multiple applications, why do you believe this will increase the chance of getting an offer? The hidden assumption is these multiple attempts has to be independent, right? If these multiple attempts, let's say you send 4 applications to 4 companies, but these 4 companies are owned by one single company, right? So in this case, yeah, you send 4 applications, but they are heavily correlated. If that's the case, you didn't increase your chance at all. Is that okay? And what you have been doing like this is called diversity. So in the context of communication, the solution roadmap is to exploit diversity. But what is diversity? So diversity involves 2 elements. Number one is you try to make use of multiple and independent. The second element is independent. Okay, let me split out these 2 points. You try to make use of multiple observations before making a decision. Remember when we talk about the modulation or receiver, we treat the receiver as a black box, right? Based on the noisy observation, you have to make a decision on what could have been transmitted, right? By the transmitter. And at that time we explained you should use minimum distance demodulation, right? because that is give you the best, highest probability to explain the observation, right? So at that time, you are making one observation, and then you make the decision based on one observation, right? But then that is not diversity. If you need to exploit diversity, you need to make the decision based on multiple observations. Okay, so first of all, you need to have multiple observations about the information being transmitted. Second of all, you need to make sure that these multiple observations, just like you send out multiple application letters, you need to make sure that these multiple observations suffer from independent fading. Okay? Just like when you send out multiple applications, you need to make sure that these companies that you apply to are not related to each other, right? When you achieve these two things, this is called diversity. Okay? So keep in mind, these are the two requirements. First of all is you need to make use of multiple observations. That means at the input of the receiver, you need to have somehow multiple observations available to your receiver. And you need to make use of these multiple observations before making a decision. Okay? In your decision-making process, you need to make use of these multiple observations. Second, you need to make sure that these multiple observations suffer from independent fading. Okay? So once you have these two conditions, then we say that you are exploiting diversity. Now, what is the benefit of diversity? I just mentioned the error probability curve, right? If you have flat fading, the curve will be like this, right? So this is under flat fading. But, so this is no diversity. Now, if you exploit two observations, and these two observations suffer from independent fading, we say that you exploit two-order diversity. Diversity order is the number of multiple observations. So if you have two-order diversity, the curve becomes something like this. The slope will be increased. So that's why diversity is a first-order solution, because it can help you to steepen the slope. Okay? So this is with diversity order of 2. If you can have diversity order of 4, then the curve is even steeper. So this is diversity order 4. Is that okay? So in other words, the slope of the error probability curve will be increased by the diversity order. Okay? And therefore, remember, the first order penalty is the difference in the slope, right? So additive white Gaussian noise have vertical slope, but this flat fading curve have a flat slope, right? So if you can increase the slope of this error probability curve, at least you reduce the differences in the slope. So this is the first order benefit. Better than those horizontal shift, where horizontal shift without increasing the slope is called second order solution. Is that okay? So the first order solution is always the slope. So that is the motivation of using diversity. When you can engage in diversity, the error probability curve becomes steeper. Okay? Steeper, that means you can reduce the SNR penalty, and that means you can reduce the coverage penalty for the coverage perspective, as well as capacity penalty. That is something we will talk about later. Okay, so the solution roadmap is diversity. So next, I'm going to talk about two things. Basically, there are just two questions. Question 1, how to create diversity observations. That is to say, to exploit diversity, the receiver needs to have multiple independent observations available, right? How would that be possible? How can the receiver able to observe multiple independent observations, right? So how? This is the first question. Second question is, let's say the receiver for some reason can have multiple independent observations. Then how to make use of this diversity observation? So what happens inside this black box? When you have multiple diversity observations available to your input, how do you make use of them before making a decision? Okay? So these are the two core questions we're going to explain. And after this, after we finish talking about these two core questions, I will end this topic with a case study, and that is a real case in a early days Wi-Fi chipset design. Yeah, okay, so that would be the topic, the agenda. And at this point, this is a convenient point to break. So let's have a 15 minutes break, and then we come back to continue our journey. Worst case is所以我们要做的就是 maximize 这个利益，然后我的左边呢是看要不要求所以第一个问题是因为我们就是这样，就是16PSK 的问题，今天也是同一个目标很清楚。我们优化的点是16个点，但是这16个点有另外完全16PSK 的需求。所以我们两个都是解同一个优化目标函数，它的区别就是那个domain大小不一样，这个domain是大于这个domain，这个domain就是你的自由度，因为这里你每一个你都要两个自由度，你可以看这是耗费的那个装备，这16QAM 里面那个都可以，它耗费的装备但是16PSK 呢，它不行，16PSK 你10个点一定要在一个度两点，所以每一个点虽然是目标，但是这个超了。所以你其实只有一个自由度，所以这个domain是小于这个所以这个问题domain大一点，当然可以做得更好。
所以我感觉这个人才想法就是下部分人可能他这个 因为它这个是相关，应该它是会发生在什么样子？他们就是这个时间和时间。然后下面就是那个经过我们的时间的那个，是的，经过。不是三头啊，是经过。我操！不是，我不允许。为什么能靠前？我们是因为我们没有钱，把什么东西？可能因为你吧。
Testing. Okay, let's get started. Okay, so let's explore the first question together. So how do we create so-called diversity observations? Which means, how do we have these multiple independent observations available at the input of the receiver, right? So So let me give you one example, and then you can generalize. So the first example I can think of is, okay, so at the transmitter, okay? So suppose I'm using BPSK as an example. Suppose the BPSK transmitter now wants to send a symbol S, okay? But send it over multiple times. Okay, send it over 2 times, let's say. Okay? So in the first transmission, it will induce one observation, which is given by the fading coefficients times the transmitter symbol. I'm using vectors in this case, 2-dimensional vector, let's assume, plus the noise. Okay, so that's my first observation, right? In the second transmission, it will induce a second observation, right, at the second time, which is given by alpha 2s plus n2. Is that okay? So now I have, by repeating the transmission of the same symbol 2 times, I created 2 observations, right? And these 2 observations will be available to the receiver at 2 different times, right? Okay? So now I created 2 observations. But then this is almost the diversity observations, except that we need to check for 2 things. We need to check for one thing, right? In order to be called diversity observations, we need to make sure that these 2 observations suffer from independent fading, right? That means alpha 1, alpha 2 must be uncorrelated. Is that okay? So how do we make sure that this alpha 1 and alpha 2 are uncorrelated? Now, if they are correlated, that means if this one suffers from deep fade, just like when you apply to the first company, if the first company is not so favorable, then if the second company is heavily correlated, then that means that the second company may likely reject your application as well, right? So then how do we make sure that this alpha 1 and alpha 2 are independent? Even if this is deep fade, it doesn't affect the chance that this is in deep fade or in good shape, right? Remember when we introduced coherence time, right? We say that the correlation between these 2 fading coefficients would be small if the time separation is sufficiently large, right? How large is sufficiently large? Larger than a parameter called coherence time, right? This coherence time depends on what? This coherence time depends on the mobility, right? It's inversely proportional to the Doppler spread. Remember that? Okay? So we just need to make sure that in this scheme, I need to separate the 2 times of transmission sufficiently large in order for these 2 fading coefficients to be independent from each other. So then I would get 2 distinct chance in the uncorrelated chance of transmitting my symbol. Is that okay? So how far is sufficiently far? Depends on your environment. So that means if you are designing the system for pedestrian user, as I said, right? So usually the mobility is low. So that means the coherence time will be longer. So typically for pedestrian user, for pedestrian mobility, the coherence time is of the order of 50 milliseconds. So that means you need to separate the 2 times of transmission by at least 50 milliseconds in order for these 2 fading coefficients to be uncorrelated. So okay. On the other hand, for vehicular mobility, let's say those users on the train, for vehicular mobility, talking about a few hundreds of km per hour, the coherence time is of the order of 1 millisecond. And that means you just need to separate the 2 times by 1 millisecond, and that will be sufficient. Is that okay? So that will be the condition. So at that time when I introduced coherence time, I didn't say anything good or bad about uncorrelated fading. But in the context of diversity, we want uncorrelated fading. Because with uncorrelated fading, it gives us independent chances. Just like when you apply for jobs, you would like these multiple applications have independent chances for the same reason. Okay? Now, in this way, we created 2 diversity observations, right? So we can name this scheme. These 2 diversity observations are coming from what? Are coming from the time dimension, right? So this is called time diversity. Is that okay? So we created these 2 diversity observations from the time dimension. So that's why we call this time diversity. Okay? Now, this is one way, but that is not the only way, right? So can you think of another way to create two diversity observations? Well, we talk about time dimension, right? So the other thing you can extend, maybe frequency dimension, right? What about frequency diversity? It's the same. Basically, in this case, the transmitter just transmit BPSK symbol 2 times, but over different frequencies, different channels. So this is one channel, and then this is the second channel. Is that okay? So when I transmit over the first frequency channel, I get one observation. When I transmit over second frequency channel, I get the second observation, right? So I have also created 2 observations. These 2 observations contain the same symbol being transmitted. Is that okay? So we are almost there. But in order for these 2 observations to be called diversity observations, we also need to make sure that they suffer from independent fading. So how do I guarantee they have independent fading? In this case, the frequency separation needs to be sufficiently large, right? How large is sufficiently large? It has to be larger than a parameter called coherence bandwidth. Remember, that's how we define coherence bandwidth. So coherence bandwidth depends on what? Depends on the multipath, right? Depends on the environment. Okay? For example, if we are talking about indoor propagation, coherence bandwidth for indoor is of the order of megahertz. Coherence bandwidth for outdoor is of the order of 100 kilohertz. These are typical values. Okay? So that means if this system is designed to operate in outdoor, like GSM system, like 3G, then this frequency, the coherence bandwidth we are talking about is only 100 kilohertz. And that means this frequency separation just needs to be around 100 kilohertz, and that would be sufficient. If this system is designed for indoor, like Wi-Fi, then this coherence bandwidth would be 10 times more, like megahertz order. And that means this frequency separation needs to be at least megahertz separation. Is that okay? All right, so again, at that time, when we introduced coherence bandwidth, we didn't say anything good or bad about small correlation. But now we want small correlation for diversity purpose. Okay? And the reason is the same as when you apply for multiple jobs application. You want each operations suffer from independent process. You don't want them to be correlated. Is that okay? So these are 2 ways, at least 2 ways that you can create 2 diversity observations available to the receiver. Now we haven't talked about at the receiver, how do you make use of this? But that's our second question. But let's worry about the first question first, right? So these are the 2 ways that you can create 2 diversity observations through the receiver input. Is that okay? Now let's focus on these 2 and see what are the pros and cons, okay? How should I put this? Okay. Now for time diversity, let's say. Now both of this design, in this example, give you two order diversity, right? So that means the error probability curve will have the slope double, like this case. Okay? It doesn't matter these 2 order diversity are coming from time or coming from frequency. The error probability curve will have the same slope. The slope only depends on the diversity order. That means only depends on number of diversity observations available. Okay? If you have 2 diversity observations, you have double the slope. If you have 4 diversity observations, the slope is increased by 4 times, like this. Okay? It doesn't matter whether these diversity observations are coming from time or frequency, or combinations. Okay, but now in practical implementation, there are different considerations. Now, first of all, for time diversity, the good thing about that is the error probability curve will be steeper, right? Steeper means you reduce the SNR penalty, and then you can reclaim or you suffer less loss in your coverage, right? So that's the good thing about having diversity. But do you pay any costs? Let's say time diversity. What's the price? There's no free lunch, right? So what's the price you have to pay here to engage in two-order time diversity? Is it free? Now just think about this. If you do not need to worry about diversity, you just need to use the channel one time to send one symbol, right? Let's say this is BPSK symbol. You just need to use the channel one time to send one symbol, right? But now with this design, to send one symbol, you need to use the channel two times, right? So in other words, the effective symbol duration, effective symbol rate would be reduced by half, right? Let's say your symbol duration is 1 millisecond, okay? So originally, over 1 second window, you can send 1,000 symbols, right? 1,000 millibars to the other side. But now, because of this engagement, time diversity, okay? You can, over 1 second, you can only send 500 independent symbols instead of 1,000 independent symbols. Is that okay? So you suffer from 50% loss in the symbol rate. So there is one metric called spectral efficiency, which is the bit rate per bandwidth, okay? So in this case, your spectral efficiency is reduced by half, right? Because the symbol rate, the bit rate will be reduced by half. That's the price you have to pay in time diversity. What about frequency diversity? In frequency diversity, if you don't have to worry about diversity, you just need to use one channel to send one symbol, right? But now, to engage in frequency diversity, you need to use two channels, two frequency channels to send one symbol. So that means your bandwidth is double. Is that okay? Previously, if you don't have diversity, the bandwidth needed is only 1 over TS, right? As we talked about earlier on. But now, to support this frequency diversity scheme, you need 2 times 1 over TS as the bandwidth. Is that okay? So that means the spectral efficiency is also reduced by half. For time diversity, is the numerator suffer from 50% loss. For frequency diversity, is the denominator having 2 times the bandwidth. So overall, the spectral efficiency is dropped by 50%. Is that okay? So that's the cost you have to pay. Okay, so moreover, they have different implementation constraints. For example, let me erase this. Now suppose I give you a toy situation. So let's say I need to design a wireless system to support real-time applications. So let's say this is for real-time video streaming. Okay, so because this is real-time, so there is a deadline constraint. Let's say the deadline is 20 milliseconds. That means when you deliver a packet to the other side, if you decode the packet more than 20 milliseconds later, that packet will be useless. Okay, so there is a deadline constraint for real time. And let's say this is for what? A pedestrian user. Okay, this system is only for pedestrian user, pedestrian mobility. So as I said, the implication is for pedestrian mobility, the coherence time is of the order of 50 milliseconds, right? Because they're slow-moving mobile. So in this case, and then at the same time, between the transmitter and receiver, you suffer from this frequency flat-feeding channel. So if you do not do anything about this, the coverage will be too short, okay? So now you want to propose a solution to fix the coverage issue, okay? So of course, you know you should engage in diversity, right? So with this constraint, what can you do? Can you do time diversity? And let's say you figure out from the link budget, with the two-order diversity will be sufficient. The question now becomes, how do you obtain two-order diversity, right? Now, at this point, we only talk about time or frequency. So can we do time diversity? Why not? Now, with time diversity, obviously it violates the deadline constraint for the real time. Why? If this is a transmitter, for time diversity, I need to send the same symbol 2 times, right? And in order for that to be a diversity observations, the time separation needs to be larger than what? The coherence time, right? So that means at least 50 milliseconds. So that means these 2 transmissions need to be separated by at least 50 milliseconds, right? Now, but if you do that, let's look at the receiver. At the receiver, what do we mean by delay or latency? So let's ignore the propagation delay, ignore the processing delay, okay? So in the best case, when you transmit S1, when you transmit the S for the first time, let's say ignoring the propagation delay, the receiver at T1 will pick up Y1, right? At this point. Can the receiver start demodulation at this point? Can the receiver start demodulation right away? No, right? Because if you start demodulation, you are only making use of 1 observation. You are not making use of 2 observations. That means you are not utilizing diversity, right? To utilize diversity, as I said, right, you need to make use of these 2 observations, 2 diversity observations before making a decision, right? So that means you need to wait for Y2 to arrive. Only at this point of time you can start the demodulation, right? Understand? So this is a timing diagram. Even if I ignore the processing delay, so let's say the processing delay is very small. So the best case delay would be, this is the time I transmit. This is the time, best case time I can obtain the receive packet, right? So this time from this need to be at least 50 milliseconds, right? And in that case, the delay would be at least 50 milliseconds, which violate the deadline requirement, right? So that means I cannot rely on time diversity to do this job due to this real-time requirement. Is that okay? How about frequency diversity? Can I rely on frequency diversity for this? Of course, yes, right? Because for frequency diversity, I'm going to send the same symbol twice simultaneously on 2 different channels, right? So these 2 transmissions happen at the same time, but on different frequencies, right? So that means if you look at the timing diagram, at T1, the receiver will be able to capture both observations from 2 different frequency channels simultaneously. Is that okay? So the latency can be arbitrarily small. Is that okay? But for frequency diversity, the requirement would be my bandwidth, these 2 channels has to be sufficiently separated, okay? So that depends on the bandwidth I have. That depends on the license, etc., okay? So in practice, for example, in the examination, I'm not saying I will, but I may, if I like, give you a situation like this, pose lots of this user requirement with different constraints, and then ask you to work out what is the problem in coverage. So how much coverage will be, are you able to meet the coverage requirement, blah, 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 blah. And then identify this coverage problem and then try to figure out how much diversity order do we need, right, to address this coverage problem. And then let's say you figure out it's 2 diversity. Let's say you figure out it's 4 order diversity. Then I may continue to ask you, then propose a scheme that can achieve the 4 order diversity, right? And the 4 order diversity may be coming from time only, or may be coming from frequency only, or may be coming from both time and frequency, right? So that is one example that I told you in the first lecture, that that kind of question is something I like, a situation, right? So, and that's why I don't worry too much about you bringing an A4 size cheat sheet, because that's not going to help much if you don't understand this. Is that okay? So I will give you different sorts of constraints. So that's why it's important for you to understand for each of this scheme, what are the constraints. So time diversity, obviously the constraint is this time separation needs to be sufficiently large. And you need to be mindful whether this time separation will violate any real-time constraint. For frequency diversity, this frequency separation needs to be sufficiently large, and you need to be mindful whether this requirement will violate any bandwidth constraint you have. Okay? Yeah, things like this. Is that okay? Now, so it seems like in time diversity and frequency diversity, it's not that ideal because you need to pay the cost in the performance, in the spectral efficiency, right? You need to suffer from 50% loss in the spectral efficiency, and that's not too good. So do we have a third way to create diversity observation? We have explored time. We have explored frequency. What are the other resource dimensions we potentially can make use of? Space, right? Very good. Space. So let's try space. Now for space, we have two versions. This is called spatial diversity. Now for spatial diversity, we can have something called receive spatial diversity. That is, we install multiple antennas on the receiver. So let's say at the transmitter, we have one single antenna. At the receiver, we have two antennas. Let's say something like this. Okay? Now in this way, the transmitter just send out the symbol, information symbol S. Let's say S is the constellation point from BPSK, let's say, okay? So transmitter just send out the transmitter symbol as usual. Now since now the receiver has two separate antennas, the first antenna will pick up one observation. Second antenna will pick up a second observation. These two observations, of course, contain the same transmitter symbols, right? But they suffer from different fading, alpha 1 and alpha 2. Now, so in this way, we created two observations at the input of the receiver by these two receive antenna, right? And there's one more thing we need to double check. We need to make sure that this alpha 1 and alpha 2, the two fading coefficients are having small correlation. So what is the condition for that to be possible? We need to make sure that these two observations suffer from independent fading. Once again, this is the same as you want your multiple job applications undergo independent decision process, right? So how do we make use of, how to guarantee this? Now this is something we haven't talked about seriously, but we can infer from this, it's very similar. In the time diversity case, what is the condition for independent fading? The time separation in time needs to be sufficiently large, right? How large is sufficiently large? The time separation needs to be larger than coherence time, right? So this is the time separation, which is a transmission parameter. This is coherence time, is the environment parameter driven by mobility, right? For frequency diversity, how do we guarantee independent fading? In this case, the frequency separation needs to be sufficiently large, right? How large is sufficiently large? Larger than a parameter called coherence bandwidth, which is also an environment parameter here, right? So here, what can you guess? How do you guarantee independent fading in the spatial situation? Something needs to be sufficiently separated, right? What is that something? Here, in time diversity, is the time separation. In frequency diversity, is the frequency separation. Now, this is spatial diversity. So what would be the separation we are referring to? Spatial separation, right? What is spatial separation? Spatial separation of these two antennas, right? Is that okay? So this spatial separation needs to be sufficiently large, right? How large is sufficiently large? In time, there's a parameter called coherence time. In frequency, there's a parameter called coherence bandwidth. Now, in spatial, there's also a parameter called coherence distance. This is called coherence distance. This coherence distance also depends on the environment. Now, again, everything is very symmetrical. In the time coherence time is actually inversely proportional to the Doppler spread, right? Spread in frequency. in the frequency situation, coherence bandwidth is inversely proportional to the spread in what? Spread in delay spread, right? So here is a same pattern. The coherence distance is inversely proportional to the spread, but this time the spread is spread in angle spread. Now what do we mean by angle spread? So if let me draw a picture. So if this is a base station, let's take a bird's eye view. Okay, let's imagine we are a bird looking down below. So this is a base station transmitter. Okay, this is the mobile receiver. Let's focus on the mobile as a receiver. So between the base station, now base station transmitter is usually mounted on the rooftop of some tall building. So if you imagine you're standing at the base station, you look around, you don't see many tall obstacles surrounding the base station, right? So usually because it's in high elevation. On the other hand, mobile receiver is at the ground level, low elevation. If you look around, you don't see the base station, but you see scattering clusters surrounding the mobile station, right? So in between the base station and the mobile station, there is some scattering cluster, like this, okay? So that's why you don't see the base station directly. You see the scattering clusters. So signals, if you are talking about mobile receiver, so signals from the base station will reach the mobile receiver through the scattering. Okay? So to the mobile receiver, the angle spread, the signal receiving from the base station will be coming from 360 degrees. Okay? So in this case, we say that the angle spread for the mobile is 2 pi. Is that okay? So that's why it is in this kind of a dense scattering environment, it is meaningless for the mobile to have beamforming. I remember in some 10 or 15 years ago, I noticed in Taobao, they sell some sticker that if you stick this to your mobile handset, they claim that they have some beamforming function with the sticker, so it helps to enhance your reception. But if you are in this environment, so it doesn't make sense to do any beamforming because the signal is coming from 360 degrees. The best way to receive signal from the base station is just an Omni antenna, okay, for this reason. Now, so this is the downlink situation. The angle spread at the mobile is like 360 degrees. On the other hand, if you look at the uplink, so if the base station becomes a receiver, then you just reverse the arrow. Signal from the base station transmit to the mobile, signal from the mobile station transmit through these scattering clusters to the base station receiver. And in that case, if we reverse the arrow, this is the angle spread at the base station. And angle spread at the base station is usually pretty narrow. For example, in New York City, they did some field test measurement. The angle spread at the base station receiver side is something around 30 degrees. It's pretty narrow. It depends on the structure of the scattering environment, okay? So the implication, since the coherence distance is inversely proportional to the angle spread, so that means the antenna separation at the mobile side, because the angle spread at the mobile side is largest, 360 degrees. So the distance separation at the mobile side is just half lambda. So this is a magic number. Half the wavelength separation will be sufficient for you to pick up independent fading. But the spatial separation at the base station will be much longer because this is the angle spread is much smaller. So usually, depends on for New York City, it's around 10 lambda. Okay, so at the base station side, if the base station is the receiver, the separation of the base station antenna needs to be at least 10 times the wavelength. So don't take this half wavelength as the holy grail. It depends on the angle spread. The half wavelength is under assumption of homogeneous scattering. Is that okay? So that is something we haven't seriously talked about, but now just for completeness, let me introduce these parameters. So in order for us to have a diversity observations, the spatial separation of the, let's say, mobile receiver needs to be at least half lambda, okay? So if you maintain this condition, then this fading coefficient will be independent. Then you created 2 diversity observations. Is that okay? Now, so this is the third way to create diversity observations, right? But then if you compare this design with this time and frequency diversity, now time diversity, you need to sacrifice the spectral efficiency. You only get 50% of the spectral efficiency. Frequency diversity, similarly, you also get 50% of the spectral efficiency. But for received spatial diversity, what is the spectral efficiency here? You got 100% spectral efficiency. Why? Because you look at the scheme. Transmitter just need to use the channel one time to send the symbol as usual. It is the receiver having two receive antenna that pick up independent observations yourself, right? This is like in the analogy. I'm the transmitter. I'm talking as usual, right? I don't need to worry about, so you are the receiver. Let's say you have 2 ears, pretty much like the two receive antennas. When I talk to you, I don't need to worry about how many ears you're using, right? You may be using your left ear, your right ear, or both of your ears. But regardless of that, I'm talking in the same way. I'm just using the channel one time to deliver one independent symbol, right? So if you have 2 ears, you will get benefit from having this two-order diversity. If you have 4 ears, you will get extra benefit from having this 4-order diversity. But as a transmitter, I don't need to worry about how many ears you have. You understand the scenario? So because of that, there's no penalty on the spectral efficiency. You have 100% throughput and full diversity. In this case, two-order diversity. Okay, so this is very good. So that's why earlier on, I think in the 60s, that's the time that people start to realize the advantage of received spatial diversity. And this received spatial diversity has been deployed since 60s. Okay, so now it's almost in every single systems. Moreover, it has also another advantage. This is transparent to the transmitter. As I said, right, the transmitter does not need to be aware of you using diversity observations, right? You can use your 2 years or 4 years or whatever number of years to receive my signal, but I don't need to worry about how you receive the signal. I just transmit in the same usual way. So transmitter, you don't need to change the transmitter, in other words, okay? And that gives you a very important advantage. Well, whether it's advantage or not, let me elaborate. So that means this is standard independent. That means you can apply this solution to any standard. You can use this to improve the coverage of GSM, Wi-Fi, 3G, 4G, whatever. Okay? You don't need to change the standard. Now, in order for you to comprehend this feature, I need to first explain the notion of standards, right? You heard about standards, right? For example, 4G have a standard called LTE. 5G, basically, they are all the cellular systems. They are all standardized under a community called 3GPP. Okay, Wi-Fi is standardized under IEEE 802.11. So modern communication systems have some standards. So first of all, why do we need standards? Why do we need standards? So what's wrong if there were no standards? Let's say in cellular system, what would be the problem if there were no standards in the world? Why do we need to conform to a certain standard? What's the purpose of standard? If there were no standard, okay, so what could you imagine? If you buy a phone from vendor A, now if there were no standard, that means everything is proprietary, right? So that means if you buy a transmitter from company A and you buy a receiver from company B, do you expect them to be able to talk to each other? Unlikely, right? Because each company will have their own proprietary way of communication. So if that's the case, if there were no standard in this world, then you got to buy the transmitter and receiver in pairs from the same company, right? Now, in the context of cellular network, that means if you want to subscribe to, I don't know, China Mobile, And let's say China Mobile purchase the base station from Huawei. Then you need, as a subscriber, you need to buy the mobile from Huawei only in order to be able to talk to the base station from China Mobile. You understand what I mean? If you buy the handset from Apple, then they may not be able to talk to the base station in China Mobile. Is that okay? So understood, right? So the primary purpose of standardization, let me erase this. So the primary purpose of standardization, is to promote something called interoperability. That means transmitter and receiver from different companies can talk to each other if they conform to the same standard. This concept is called interoperability. Is that okay? That's the purpose of standardization. And as I said, in mobile communication, the community enforcing the standard is called 3GPP. Okay? So interoperability is the primary purpose of standardization. And that's the reason why we want to have standard in this world. And with interoperability, you can use, I don't know, company B's mobile, despite the operator is using company A's base station. As long as they've conformed to the same standard, they can talk to each other. Is that okay? And therefore, as a subscriber, you find it very convenient, right? You also promote competition. You don't need to confine by the vendors of the base station. When you choose your handset, you can have your own independent choice of your handset, and you will still be able to talk to the base station of a certain vendor. Okay? Now the question is, how do you achieve this interoperability? Now one naive way is the standard specify everything in the transmitter and the receiver, right? If the standard try to specify everything from the transmitter all the way to the receiver, for example, specify what kind of modulation you use, specify how you do channel estimation, how you do demodulation, etc., right? Then of course, in this case, you can achieve interoperability, right? But what's the problem of this naive way? If the standard specify every single details in the transmitter and receiver, what's the problem? Now, in this case, imagine you're the handset manufacturer. Do you like this? If this is the case, do you have any room for innovation? There's pretty much no room for innovation, right? The handset produced by company A or company B will be identical in performance, right? Because you pretty much specify everything. There's no freedom for deviation. If that's the case, this is called over-standardization. Then yes, if you do this naive way of over-standardization, you can achieve interoperability, right? Because they are functionally the same handsets. And in this case, different vendors will have no rooms for competition by performance. They can only compete by having different price level, different design of the handset cases, and this kind of superficial stuff. They cannot compete on having different performance because there is no room for them to have different design. You understand what I mean? So, on one extreme, over-standardization is not an option. It's too much, right? With over-standardization, when you specify every single pieces of details, you leave no room for the vendors to innovate, and that is bad, right? They cannot compete by performance, right? So the art of standardization is, on one hand, you want to make sure they can interoperate with each other. On the other hand, at the same time, you want to leave sufficient space for different vendors to have different innovation so that they can compete with different performance. That means you don't want to specify everything. You want to leave as much room as possible, provided that they can still interoperate. Understand the trick? So usually, the way to do that is, in the transmitter side, they usually specify a lot of details. So there is little room in the transmitter. They need to make sure that the transmitter format, the transmitter signal, the frame format, everything that you transmit will be standardized, right? Because otherwise, then it's difficult if the transmitter from company A and the transmitter from company B send out the frame format are also different, then it is very difficult for you to be compatible to 2 transmitters, right? So usually, to achieve this, the transmitter usually are tightly specified. But on the other hand, the receiver usually how you do the demodulation, how you do the channel estimation, how do you take the observations and process to get the output. These kind of details are outside the scope of standards. So standards usually will not specify too much how you do receiver processing. Okay? They just need to make sure that the radio interface, the frame for the data, the frame for the signaling, they conform to some requirement. Okay? And otherwise, how do you, from this, if you're the receiver, you're the input, you are presented with the standard frames. As long as this frame that you perceive is standardized, then the standard doesn't need to care or worry about how you receive, how you demodulate this information. So usually, the transmitter are tightly specified. The receiver are loosely specified. That's when you read different standards, you will usually have this kind of pattern. The reason for that is they want to leave sufficient room for innovation, for different algorithms, so that different vendors can compete by having different performance. Is that okay? So that's the standardization. Now, the thing is, I said that now if you compare the 3 diversity schemes that we talk about, time diversity and frequency diversity, if there were no such design beforehand, and let's say you are the first one to propose this design, do you need to change the transmitter? Do you need to change the way that the transmitter transmits the symbols? Of course, right? Because for time diversity, if there were no diversity, the transmitter just send one symbol once, right? But now you engage in time diversity, you need to send the same symbol twice. So you need to specify how you send the same symbol twice and different frame location, whatever, right? Same for frequency diversity. You also need to specify how you transmit the frames at different frequencies, etc. So these 2 designs, time diversity and frequency diversity, you need to change the transmitter. If you want to change the transmitter, that means in order to adopt your solution, you need to change the standard. Is that okay? Now, changing the standard is quite tedious. As I said, the standardization part is based on 3GPP, right? So 3GPP is a consortium. So the members of 3GPP usually involve chipset vendors, handset vendors, infrastructure vendors like Huawei, and also operators like China Mobile. So these are the major players within 3GPP. So, okay, so different vendors, in order for a particular proposal or contributions to be adopted to be the standard, you need majority support in the standardization committee. So the way they work is for 3GPP, every company only have 1 vote. It doesn't matter you have 10 engineers or 100 engineers into the standardization meetings. You only have 1 vote. Every company only have 1 vote. So in order for your contributions to be adopted to the standard, you need support of your competitors, okay? So that's not easy. So a lot of times, you need to have the technical side, from my experience, the technical side only account for less than 10%. The other 90% are based on your political and other strategic consideration. Now, what are the strategic considerations? Why companies want to propose something into the standard? So to explain this concept, I need to introduce a concept called standard essential pattern. Okay, let me sidetrack a little bit. You heard about patents, right? So if you invent something, right? So the typical story was like, the fairy tale was like, you invented something. So you want to protect your invention. So you go and apply for a patent, right? Okay, so let's say as a student or as an individual, you have some great invention. So will you go and apply for a patent? First of all, it's not free. So if you want to apply for a patent, file a patent, even if the patent is granted, you need to pay annual maintenance fee, which is also not cheap. Okay, so you may think about applying for filing a patent, right, in order to protect your invention. But if you think deeper, so what's the purpose of filing the invention? For protection? Now imagine one day, let's say a big company, like your invention, okay? Do you think this big company will go and talk to you to license your patent? You wish this will happen, right? But reality is, if there is a big company, they like your patent. Let's say they implement your idea without licensing from your patent. What can you do? You sue them. So if you want to sue them, patent litigation, first of all, is a very lengthy process. It can take decades, 10 years. And it will involve many rounds of proceedings. The company, if they're a big company, they usually have a big legal team to do this. If you're on an individual basis, in order for you to engage in a patent litigation, you need to have a lot of money to pay for the litigation costs. You need to engage in multiple lawyers, attorney, and go through multiple rounds of litigation. And at the end, there's no guarantee that you will win. Okay? So with this realistic picture, will you still sue the company? Probably not. You have to sell your house and borrow money from your friends and family in order to engage in this 10 years long of patent litigation. And at the end, the outcome is still uncertain. Will you do this? Probably not, right? So patent is not for individual. My own experience. So what is the use of patent? Patents are for company. If you have two big companies, company A, company B, when company A want to sue company B with the patent infringement, usually company B will sue company A in return, okay? And if both companies have this patent portfolio, at the end they will settle by this kind of cross-licensing, okay? So usually, big company will not be interested to sue another big company because at the end it's just a waste of time, okay? The other side will sue back. So usually the patent is, the game of the patent is usually big company would like to sue small company. If you're too small, they are not interested. If you are some kind of not too big but not too small, then they will be interested in suing you. The reason is for the same mechanism. They know that if you, let's say you start a business making a mobile phone, right? And let's say you grow to a medium size with very good fortune, start to earn quite a lot of money. And one day, a big company send you a letter asking you, saying that you are infringing their patent number 1234, and ask you to pay the license fee. And then you look at the letters, you find that this is ridiculous, this is nonsense. I didn't, of course, the first reaction is I didn't infringe your patent, whatever, right? But at the end, what can you do? Now, you can say, okay, I didn't infringe your patent, I can go through the litigation. But don't forget, the big company has a whole team of legal employees. Their job is to find companies to sue. And you are just a medium-sized company. Are you able to afford the litigation costs? And moreover, the big company, the license fee they asked for, they did some calculation before. It would be usually cheaper than your patent litigation costs. So in this case, it will have a tough decision to make. So patent is for this application, okay, for this kind of situation. It's a big company trying to sue small company. Okay. Now, in the patent litigation process, okay, I'm trying to explain standard essential patent. In the patent litigation process, of course, the different, so usually if a company wants to sue you for infringing the patent, the burden of proof of infringement is on the plaintiff side. That means the one who sues you needs to have the responsibility to prove you have infringed the patent. So how do you prove? Now, if the patent is about a particular algorithm in communication, right, it is usually very difficult to tell or prove that you have infringed the patent. You have implemented this particular patent. Usually the way they need to do that is to buy, let's say you're a mobile phone manufacturer. Usually the plaintiff has to buy the mobile phone from you in secret. And then they have to reverse engineer your chipset, reverse engineer your code, and from these, recover the algorithm that you're using and then argue that this algorithm is protected by that patent. But reverse engineer is very expensive, right? So for a regular patent, especially those related to algorithms, it's not that easy to find infringement proof. That's very costly. And for that, that will decrease the value of a patent. Because if it's very difficult to execute the litigation, then there's no value on these patents, right? So the value of patent is not about how complicated your algorithm is. Okay, it's never the case. The value of a patent is how easy it is to find proof of infringement. Okay, so for communication-related patents, okay, one easy way to find the proof of infringement is if this particular patent, if this particular idea is adopted into the standard. Okay, if let's say this particular invention is adopted into the LTE standard, then it's a different story. Then in this case, the proof of infringement, if I want to prove you infringe my patent, I just need to prove that your mobile phone conform to LTE standard. Because by definition, my patent has been adopted into LTE standard. So if your mobile phone conform to LTE standard, your mobile phone must infringe my patent. You understand this logic? Proving a phone conform to LTE standard is very easy. You have lots of testers out there for doing this. Okay? So that's why a lot of vendors, they would like to try their very best to push their patent. Usually, before they push something into the standard, they will have some patent ideas already. They file patents already. And they will have the interest to push some patent invention into the standard. Because once this invention is into the standard, that patent will be very valuable. And that patent becomes something called standard essential patent. Okay? So different vendors, 4G, 5G, whatever, when they count the number of patents, usually what matters is not the number of patents. What matters is the number of standard essential patents. Okay? Because that would be something very valuable due to easy to prove infringement. Is that okay? Now, so back to this point. Now, if you want to implement this idea, this is an innovation to improve the coverage, right? You create diversity order with 100% spectral efficiency, no loss, right? So very, very good. And also, this is transparent to the transmitter. That means you do not need to change the standard to implement your idea, okay? Now, whether this is good or bad depends on your company. If you are a small to medium-sized company, okay, playing this standardization game is very expensive for the reason we just explained, right? Because you need to have sufficient number of teams into the standard so people have to know you before there is any chance for people to support your contribution. Because there are a lot of interest behind the scene, okay? Every company wants to push their patent idea into the standard. So if you're just a small company, nobody will pay attention, okay? So if you're a small company, you work for a small company, if you think of some solution like this, then this is very good because you can avoid getting into this expensive standardization game and you can still implement your idea to improve the performance of your product, okay? So that would be something very good. But if you work for a big company like Huawei, if you have an idea like this, that may not be good. Because for Huawei, the major goal is to increase this standard essential patent. So if you patent this idea, but this invention has nothing to do with standards, then this patent will never be a standard essential patent, and that patent will not have the same kind of value as standard essential patent. You understand my point? So if you work for big vendors, they will prefer having innovation that have the opportunity to push into the standards. Okay, so whether this is good or bad depends on who you work for. But what I just want to point out is this receive spatial diversity has this advantage: 100% spectral efficiency, full diversity order, and moreover, you can implement this without changing any standard. Okay, so any questions? Okay, so this is receive spatial diversity. Now, this is not the only way to engage in spatial diversity. The other way is transmit spatial diversity. How about you put multiple antenna on the transmitter side? Now, I don't have time to go over this. But it turns out that you may think that this should be symmetrical, right? But turns out that this is not symmetrical. So this has been around since 60s. And then people start to think about, the motivation is, okay, as I said, the multiple antenna on the receiver side needs to be sufficiently separated by half lambda. So in 3G, the carrier frequency is 2 gigahertz. So a wavelength is like 15 centimeters. So half wavelength is like 7.5 centimeters. So, but on a handset, you have limited wave estate. So you cannot put too many independent antennas on a handset. So because of that, you have a limited size on a mobile device. You may think that, how about I put up multiple antennas on the transmitter side? The base station side usually have more space, right? Because you're mounted on the rooftop. You can have more space to install more antennas on the rooftop. So that was the motivation of considering multiple antennas on the transmitter side. And what they hope to achieve is this is called transmit spatial diversity. When you have transmit spatial diversity, what they hope for is you can still achieve 100% spectral efficiency and full diversity order. But turns out that people have been studying this for decades, and they couldn't figure out any solution that can achieve this goal. So the earliest solution that can achieve this goal is end of 90s, okay? So, and that's called the multi-scheme. So I will explain the details next time. So I guess this is let me stop at this point, okay? And I'll see you next week.